Good morning, everyone.
Good morning.
I want to talk to us today about investigating Earth's boundary layer from the ground and in the air. One of the things that I've often shared with audiences when I make a presentation is how important the air is to our daily lives. We can't see it, unlike the oceans, and unlike my colleague, Dr. White, who studied dolphins. Everyone thinks they are cute and wonderful. They can see them, they can sense them, but how often do we think about the air? Prior to the pandemic, I would guess not very often. Since the pandemic, I think our collective memories and our collective thought process about the atmosphere and air quality and air chemistry have probably changed a bit due to what we've experienced over the last 2 years. Part of what we do in the NOAA Air Resources Laboratory is to look at changes in the dynamics of the boundary layer. That's the layer of the atmosphere that's closest to Earth. It's where we are sitting right now. It's where we're breathing. It's where we work. It's where we play. It's where our families live. So in our viewpoint, it's the most important because that's where people are. And we heard some of that yesterday in the afternoon session with Dr. Brown and Dr. Gregg about environmental justice, ensuring that we're connecting the science that we're doing to the people in the communities that we serve. In the prior session, my colleague, Dr. Sims, showed this slide at her beginning of her talk, and I had to smile a bit. It's a slide we use as well. It's our $2021 billion weather and climate disasters. One of the things that's different that I want to point out is the office where I work is in East Tennessee. It's kind of covered by that rain cloud there for the eastern severe weather. We are closest to so many of these weather disasters. If you notice, they're kind of centered in the part of the country where we're located. And that gives us an advantage from my NOAA office because we are able to quickly deploy to the geographic location where a lot of these weather phenomena are occurring. And another thing I want you to notice is, and I'll start with a question. Where is Tornado Alley? Where have you heard about Tornado Alley? Where is that? Midwest, Oklahoma, Kansas area, right? Okay, where are all these storms occurring now?
Southeast.
Southeast. When you look at the data that's coming in from NOAA and many of our partner agencies and private industry folks, you will see that the severity of a lot of the storms has shifted from that Midwest Tornado Alley traditional area to a lot in the Southeast. And one of the reasons I want to highlight this is because what's different between the Southeast and the middle part of the country and the Midwest when it comes to topography? Who's been out in the Midwest? Oklahoma and the Western Plains, what is the topography like?
Right.
It is flat. You can see, I'm looking at Dr. Carlos here, you can see for miles out there. What about in the Southeast? We're in the Southeast right now. Can you see for miles sitting here on the highest of 7 hills? Maybe, maybe not. What also do we have that's different? Vegetation. We have a lot more trees. We have a lot taller trees. And all of that is affecting how people can actually be able to respond to severe weather events. If you're somewhere where you can see a tornado coming, it's easier for you and your family to be able to take cover and protect yourself. If you're living in the Southeast and you live in an area that's heavily forested, that has a lot of trees, that's rolling hills, most likely you're going to have a more difficult time seeing that weather event come your way. So when we talk about this, it relates to our research in many ways. In the Air Resources Laboratory, we are trying to understand and study what's happening in that planetary boundary layer. We're looking at physical processes and chemical processes. We're looking at them on the short term of what's happening in minutes and hours, all the way out to what's happening on the climate scale of decades and decades of measurements and modeling observations. We're looking at transporting, mixing, and exchange and transformation. We're doing that with observations, and we're also doing that with atmospheric models. We have 3 scientific research themes that you'll see in the photos here: surface atmosphere exchange, atmospheric transport and dispersion, and boundary layer characterization. I'll go into surface atmosphere exchange first. That's my personal favorite. That's my research area that I had conducted much of my work in, starting with my PhD days. We want to understand what's happening at the surface. And when we say surface, surface can mean the top of a tree canopy, or it can mean the top of grass or a crop that's very low. What's happening between the air that's right above that vegetation or the soil and what's happening in that vegetative canopy or at the soil? I can tell you there's a lot of dynamics going on. There's exchange of gases, there's exchange of particles. We want to be able to measure that with some accuracy and some efficiency. We also want to be able to understand what's happening in the long range, transport and dispersion. One of Air Resources Laboratory's probably most popular products that we develop is the high split model. People may have heard of the high split model before. That comes from my laboratory. We're trying to understand what happens over long range transport when we have dispersion of chemicals in the boundary layer. Where do they end up? Where are they going? We also want to understand boundary layer characterization. So we want to understand those interactions. We want to understand transport and where it's going. We also want to understand what's happening when it comes to wind direction and speed, temperature, relative humidity, surface energy balances, all of those things. And we do that through a number of measurements that we have. For surface atmosphere exchange, we're interested in those processes. For example, like I said, that exchange between the lowest part of the boundary layer and the vegetation that we have on Earth's surface. That looks different depending on where you are. If you're in an agricultural ecosystem, you may be looking at row crops. If you're in a forest ecosystem, you can have a canopy. Very few forests are just homogeneous. They're heterogeneous. They have a lot of different vegetation. What is the atmosphere like above that canopy, within that canopy of trees, as well as below it? And then we also are starting to look at coastal ecosystems, which is one of my favorite locations because it's so hard to make measurements along the coast. There's so many different dynamics going on when it comes to the atmosphere because you're not only dealing with Earth's surface and the atmosphere, you're also dealing with water. And if you're in certain areas, especially where we took this photo of equipment we deployed a couple of years ago, you're talking about tide. How are you measuring the exchange of chemicals that's happening when sometimes that surface is covered with water and sometimes it's not? This is some of the data that we have from a coastal ecosystem. It's the St. Jones Reserve, which is in Delaware. It's one of our national near sites that NOAA has. We were looking at ammonia concentrations. Anybody know where ammonia comes from and how it gets into the atmosphere? Ever thought about that? Who has lived on a farm or driven by a farm? What does it smell like?
Fresh air.
I think we have different definitions. So ammonia gets emitted from animal waste is one of the huge ones. So if you've driven by a farm, you have that wonderful fresh air odor that Dr. Carlos mentioned. That's coming from animal waste, and that's the main producer of ammonia and how it gets emitted into the atmosphere. So we use the cavity ring down system as well as a passive kind of sampler filter system in order to measure ammonia that was at this reserve site, which is a coastal ecosystem, but it's pretty much surrounded on many sides by different agriculture. What I want you to notice in the chart to the left is those orange triangles, those are our real-time measurements. We're measuring ammonia every minute with this cavity ring down laser system. The blue lines are your passive samplers. We put those out for 4 hours and let them collect data. And it's the same thing in the pink and the blue one on the right side. What you'll see is the passive samplers, they get it right on the average, right? They're right there near the mean. But look at all of what happens dynamically around that mean. This is why it's important for us to be able to have real-time measurements, because what we're missing is what that change is, how it's changing over time when we have a passive system. But don't get me wrong, I use passive systems for years. I think they're great. It's just that as the technology evolves, as many of the students that are part of the centers are developing new technology, whether you're an engineering student, you're helping us to be able to more highly resolve some of the changes in concentration that we see. Another experiment that we currently have ongoing is the SPLASH experiment, the study of precipitation in the lower atmosphere and surface for hydrometeorology. Anybody ever heard of hydrometeorology? Okay, give me a definition quickly, somebody. What's hydrometeorology? The water and what the water is doing in the atmosphere. This is one of those experiments. We're at Crescent Butte, Colorado. And we have a number of NOAA collaborators out there with us that are either taking measurements in the field as well as developing model parameterizations to help us understand what's going on. I heard someone mention this morning, we were having a conversation about how wonderfully humid it is here, right? Is there a lot of water in this atmosphere or a little water? A lot of water. What happens when storms come? Does it feel a little warmer? Does it feel a little bit more humid ahead of those storm front? We want to understand how that's happening, how that's changing, the effects it has on the vegetation as well as on the atmosphere. And then you'll see, this is the Crescent Butte area in Colorado. And then these are just some images showing where we have different measurements. And again, look at the topography of this place. Most of the experiments when it comes to field work for understanding the atmosphere many decades ago were all done over flat topography. Well, most of the world is not flat, right? Much of it looks like this. And that's why it's important for us to be in these complex terrain environments in order to be able to understand what's going on. And then these are just some pictures of our equipment out there. Students, as you're out, being able to engage in research, I encourage you to think about where you're going, take chances to go out into the field, see some of this equipment. There's nothing like going out to a site where you've got to basically hike to get out there. There's nothing like going out to a site where you have like snow on the ground and you've got to have all your gear on to be able to get out there. That makes the science real to me. It helps connect people with the science that we're doing. And then I'll talk about the Air Resources Laboratory and our uncrewed aircraft system research or drone research that we're doing. We've had presenters this morning who've talked a little bit about aircraft measurements, satellite measurements, sending up sondes with balloons. I've talked a little bit about ground-based measurements, but what we'll see in that circle in the red is how are we collecting measurements in the middle, between those upper air and between the ground? That's a data gap because we don't have a lot of good ways to collect those types of measurements. So in alignment with OAR strategy of designing tools and processes so we can understand high impact weather, understanding how we address that data gap, we're deploying a series of drones from our fleet in order to be able to measure things like temperature and relative humidity, and then the different aspects of the wind. And all of these drones allow us to take those meteorological measurements, but they all have these things of how can we attach other measurements to the drone? That's one of the questions we're addressing now. How can we perhaps measure particles in the air using these types of platforms? These are some of the sensors that we have where we're measuring temperature, moisture, wind speed. We also have some cameras on there, an IR camera where we're able to take photos of the topography as we're flying over it. Many of these are fast response sensors. I would say students, if you have an opportunity to be trained as a drone pilot, take that opportunity. This is the future of a lot of the research that will be happening, not only in NOAA, but also in other agencies and with our partners. And there are very few folks who are fully trained and certified to be able to fly. Vortex Southeast, we talked about the Southeast. This is another large experiment that the Air Resources Laboratory has been engaged in. We did ground-based measurements, we've done drones, we've done balloon measurements, and a lot of those measurements have helped us understand and try to resolve some of the differences that's happening. So you'll see here, this is some information from some simulations that we ran with the HER model, looking at temperature and humidity measurements, and you'll see how the HER model did well with the temperature, but when you come to some of those surface energy fluxes, there's some differences there. How do we take observations to help us refine those models so that they better reflect what's actually happening in the environment? So mentorships and student opportunities, and this is my last slide. I want to park here for a minute and talk about that. These are some of the photos of some of the students that we worked with, K through 12, as well as college and graduate students. We are a small laboratory. We're actually the smallest laboratory in terms of people when it comes to NOAA research. But we've had 21 formal interns just in the last couple of years that have worked with our scientists and engineers and our administrative individuals in the laboratory. to do research and help support that research in various ways. We've had interns from the CSCs, we've had them from some of our partner universities. What I would encourage students to do is if you want that hands-on component, it's been difficult during the pandemic. I mean, you haven't been able to travel to many sites to have that hands-on research experience. But what I would encourage you to do is to reach out, make connections at this meeting with people who are doing the type of work that you're engaged in. And if you can't come from an internship, can you come for a visit? Can you spend a day or two there, learning about their work, talking to people in the laboratories, seeing what they do? One of the things that I know my colleagues and I really enjoy is taking students out into the field, helping you see what you're doing. Because for me, one of the things that clicked between undergraduate and graduate school was taking what I read in the textbook and being able to see how it's happening in the environment around me. And so we can take students out, we can set up a small weather station, and they can have hands-on experience. And this is not only applicable to everyone who's already in college, but a lot of K through 12 work. One of the previous speakers talked about middle schools. That's one of my favorite grades to talk to. I have 2 middle schoolers myself, because that is the time when they're thinking about what comes next in high school. What do I want to study? What opportunities are available to me? And for so many of them, I can ask them where they get their weather from. They get it from the app on their phone. Well, how does that data get in the app? Where does it come from? Those are the types of questions that make them think more about what is behind the scenes that they may not be aware of. So that concludes my presentation. I'm happy to take any questions.
Thank you much, Dr. Myles.
Thank you.
I'm sure we have a number of questions. I see a hand up already.
Hi, my name is Dimitri. I had a question regarding the drone piloting that you mentioned. Was that the FAA drone piloting that you were referring to?
Yes, you have to go through the FAA certification.
No problem. Thank you for clarifying that.
Sure. And then if you're flying a NOAA aircraft, there is another level of certification with NOAA. If you're flying a university-owned aircraft, most universities also have some type of training or certification process for their own institutions as well. But if you can get that FAA one, I think you can sail through the rest.
Okay.
Thank you. Other questions? Colleagues?
Just a quick kind of reflection question that I asked earlier related to what would you kind of tell your younger self, being a woman of color, moving up through the ranks of NOAA, I'm sure hasn't been peaches and cream, but, what would you, when you kind of reflect back, you were part of the inaugural class of EPP program. I was just right after you. So what would you say?
I would say 3 things, and I'm glad you asked this because I heard Janice's answers and I was like, those are great answers. The first thing I would say is learn how to write a proposal. And I see Dr. White shaking her head because we have talked about this a lot. You learn so much about doing the research, but guess what? You gotta have funding to do the research. How do you write a proposal? How do you put together a budget for a proposal that accounts for a realistic estimate of people's time, the equipment that you need, the laboratory space you may have to use? And I'm not sure if they teach that now in graduate school. I didn't get taught that. So just think about talking with these professors that are instructing you guys and guiding your research on a day-to-day basis. I can guarantee you they've probably been involved in a proposal. Go back and ask them, what did it take? They'll probably have a chuckle first, and then they can go into the story of sharing with you about how to write a research proposal so that when you go on to that next step in your careers, whether it's with government or academia, you're already a step ahead in understanding how to write a research proposal. The second thing I would encourage, if you're involved in any research, whether it's through a NERTO or another internship or at your centers, be a co-author on a paper before you graduate. I know most people think, oh, everyone that's a co-author, they have done all this amazing work, they've really contributed. But if you have been involved in helping to plan or execute or implement that project, you have an opportunity to contribute to the manuscript that describes the work from that project. So going in the door, whenever I have an intern that comes to work with me, undergraduate or graduate, the first thing I tell them is my expectation is before the end of the summer, you'll be a co-author or even a lead author on a publication about our work, because that also is another tangible product from your work that can have great benefit going along. So learn how to write a proposal, ask to be a co-author on a research paper. And then the third thing I would say is don't sweat the small stuff. Everyone has an experiment that fails. Everyone has an experiment where you figure out there's some parameter that you wish you would have measured, but you didn't know about it until after the fact. You talk with the modelers and they say, I need to know about latent heat, and you didn't measure latent heat. It happens to every single scientist. So don't sweat the small stuff. Use it as an opportunity or a springboard to say, the next time I go out into the field, the next modeling study I run, I want to make sure I have that data set available to me. Thank you.